All right, so we're well into chapter 10 now, and hopefully you've been following along as we've been talking about some properties of acids and bases and their strengths and the autoionization of water, and then most recently the pH scale. So now there's not a whole lot left. In this section, we're going to be talking about the reactions of acids and bases. If you think back to the first section here where we talked about properties of acids and bases, and we talked about Arrhenius acids and bases and then Bronsted-Lowry acids and bases, there's actually, if we're using the broader definition, there's even Lewis acid-base chemistry, which we didn't get into in our course, but it really opens up many of the reactions that we would encounter to be really acid-base chemistry if we get down to it. So we're going to stick with the more classical definitions of acids and bases and the reactions that those substances have. But if you go on in chemistry at the highest levels, you'll see that there's a lot more acid-base chemistry depending on the broad definition you use for acids and bases than we might touch on here in this section of chapter 10 in our course. One of the classic reactions that acids undergo is reaction with certain metals, and the products are hydrogen gas and then the metal salt. So we see a couple examples here. First, potassium metal, a very active metal, reacting with nitric acid to form potassium nitrate and hydrogen gas. Magnesium, a less active metal, although still an active metal, reacting with nitric acid as well to form magnesium nitrate and hydrogen gas. We see the difference. There's either 1-to-1 mole ratio of the acid and the metal, or in the case of the magnesium, 2-to-1 mole ratio of the acid and the metal. But they both have the same basic scheme. They end up with the metal nitrate in this case because we use nitric acid. It would be the chloride if we used hydrochloric acid, so on and so forth. But we get that metal salt and then the hydrogen gas released. We see rapid bubbling as a result of that hydrogen being released, and of course we don't want to build up too much hydrogen gas, or it could be dangerous if we have hydrogen mixing with oxygen and getting an explosive mixture. But if it's a small scale like that little test tube, sometimes we'd even put a flaming splint over it to show that you get that pop from making water from the hydrogen and oxygen reacting. So the oxygen is just present in the atmosphere, the hydrogen is generated by this reaction, and we can prove that in that sort of demonstration. Similar to the acids reacting with metals, you can get acids to react with metal carbonates or bicarbonates, which are really hydrogen carbonates according to the new naming scheme. And in this case, in addition to getting the ionic compound, the salt that we got in the reaction of the acid with the metal, here you get carbon dioxide gas from the carbonate or hydrogen carbonate. You get water as another byproduct, and then finally the salt. So we don't get any hydrogen here. So the gas that we produce in this case is carbon dioxide gas, and it has to do with the acid reacting with that carbonate or hydrogen carbonate to make carbonic acid, which breaks down very rapidly into the CO2 and H2O that we produce. Our bodies also have ways of breaking down carbonic acid so that we can release carbon dioxide in our lungs and so on and so forth. So if you notice, the scheme is very similar. We've got the acid and then the metal carbonate. Here we have calcium carbonate or sodium hydrogen carbonate, depending if we're looking at the first or the second reaction. But both products are similar, carbon dioxide gas and water, and then the particulars of the metal salt would depend on if we're a +2 ion like calcium or a +1 ion like sodium. We would get a different formula there for the salt, the metal salt that we produce. Okay, if we wanted to prove that it's a different gas, because we just see bubbling, just like we see bubbling in the case of the metal and the acid forming the hydrogen gas, we could do the same flaming splint test that gives a nice pop with hydrogen. It doesn't support a flame when that's carbon dioxide. The flaming wood splint would be put out if you tried to do the same test here with carbon dioxide gas, because the carbon dioxide gas is already fully oxidized. It doesn't support combustion any further. So that's a nice way to prove the difference between the types of gases that might be released in an acid reacting with a metal that releases hydrogen gas versus an acid that reacts with a carbonate which releases carbon dioxide gas. Another consequence of acids is our problem with acid rain. And If you're not familiar with that phrase, I imagine most people are by now, but if you're not, it's a term given to precipitation, so that could be rain, snow, hail, fog, some sort of moisture from the atmosphere that has a pH of 5.6 or less. And this has become a problem since industrialization, where we started to have the burning of hydrocarbons for energy and sulfur impurities from coal in particular, or oil, whatever your carbon source is there. When it interacts with water and oxygen gas in the atmosphere, it forms sulfuric acid, which is one of our 6 strong acids if you think back to our second section here of chapter 10. So we see that process, the sulfur, which is an impurity in a lot of those hydrocarbon sources, or coal, interacts with oxygen, oxidizes to form sulfur dioxide. Then the sulfur dioxide oxidizes even further to form sulfur trioxide gas, which dissolves in water to form that sulfuric acid. And this is a problem. It's especially a problem in the Binghamton area. So because of the Midwest industry and the Southeast industry and where we happen to be located, again, it doesn't necessarily affect the immediate areas as badly as where the winds blow it. So it's not that we're producing a lot of these sulfur oxides in the Binghamton area, but we happen to be at the crosswinds of areas that produce it. And so we end up having a pretty significant acid rain problem here, even though we don't have much industry left. So it's the industries in the Midwest in particular that contribute to our acid rain problem. And acid rain is a problem because it'll degrade marble statues. Marble's calcium carbonate, so it will react with sulfuric acid. Limestone is also calcium carbonate and will also react with sulfuric acid. So those statues and structures can be devastated by acid rain. It'll pit the marble statuary, can cause weaknesses in the limestone structures. It also interferes with photosynthesis, so it can kill plants and trees. In the Adirondack lakes, there are some lakes that are granite lined that don't have the ability to neutralize the acid. The ones that are limestone lined can neutralize it a bit. And so you get areas where animal and plant life are compromised, and that can cause dead lakes to form, and it's really a big problem for a number of reasons. So it's something that hopefully with the more stringent use of scrubbers and other sorts of technology to limit the amount of sulfur oxide that's released, it should be getting better, but it's going to take a while because it's been going on for some time now. And again, I did mention that it is a problem of local interest for those of us in the Binghamton area, but it's not only our area. Here we see a marble statue in Washington Square Park that's been eroded by acid rain. So this beautiful statuary that was built to last, unfortunately, we found a way to compromise its beauty and integrity because of this acid rain problem. On the right-hand side, we see acid rain that's severely damaged some forests in Eastern Europe because of, again, being so significant and because of its ability to interfere with photosynthesis. It can devastate forests, and in the example I used with the Adirondack lakes, it can also affect animal life as well as plant life because of the acidity that can be achieved through that acid rain problem. Okay, so not to minimize the issue of acid rain, it is a problem, and fortunately, as I said, it has been getting better because of legislation and so on and so forth, but it's certainly something, if you're passionate about the environment and you want to do more, please do write to your representative in Congress and let him or her know that you want even stricter rules and even greater control over sulfur oxides and their contribution to acid rain. But we still have to move on. So we'll take a learning check here just to make sure that what we've discussed so far is making sense, and then we'll move on to more concepts with acid-base chemistry. For this learning check, you're asked to write the products and the balanced chemical equation for each of the following reaction of acid. So we have metal reacting with an acid, metal carbonate reacting with an acid, and then a different metal carbonate reacting with a different acid. So for each of those, if you would go ahead and show the products and continue to balance the reaction, and then pause the video here while you do that, and please start back up once you're ready to check your work. Okay, so for the first one, that zinc solid plus the 2HCl aqueous yields ZnCl2 aqueous. Zinc's plus 2 is a stable metal ion, so hopefully you caught that. Again, some of the transition metals can be unreliable, but zinc will always form a plus 2. It's one of our predictable transition metals. And then we get 1 mole of hydrogen gas generated as well. For B, the magnesium carbonate solid reacts with 2 moles of hydrochloric acid to form magnesium chloride aqueous plus carbon dioxide gas plus liquid water. And very similarly in C, we have sodium carbonate reacting with now hydrobromic acid, and that's going to form 2 moles of sodium bromide aqueous plus 1 mole of carbon dioxide gas and 1 mole of liquid water. So hopefully those were nice and simple. It's been a little while since we balanced reactions, so if you did have a little trouble, hopefully it was just getting back into the swing of things, but please do try some other problems, and if you find that you're not catching on again how to balance chemical reactions easily, please do reach out to me for some help. Probably the most important group of acid-base chemistry reactions we'll look at in this chapter are neutralization reactions. So a neutralization is the reaction of an acid, such as hydrochloric acid, and a base, such as sodium hydroxide. We just pick our characteristic acid and base here. So HCl aqueous plus NaOH aqueous yield NaCl aqueous plus H2O liquid. So this is the classic neutralization reaction. Acid plus base yields salt plus water. And if we think about the net ionic equation, we would just separate everything that's aqueous into the ions that it generates. Unless it's a weak acid or a weak base, we would keep it molecular. But in this case, since we have strong acid and strong base, we have HCl separate essentially completely into H plus aqueous plus Cl minus aqueous. The sodium hydroxide, strong base, it ionizes completely into Na plus aqueous plus OH minus aqueous. And then on the other side of the reaction, we get sodium chloride, table salt, and that is very soluble in water. So that would be Na plus aqueous plus Cl minus aqueous. And then water is our coproduct, and that stays as liquid water. So as we cross out the species that occur on both sides of the reaction in the same form, the Cl minus aqueous, the Na plus aqueous, then we get for our net ionic, so that was our complete ionic, we crossed out the originally, I should back up to where we had the HCl together. That we call it the molecular equation. Then when we split it up into ions, we call it the complete ionic. Then after we cross out those spectators, the species present on both sides in the same form, we get the net ionic equation. So for acid plus base yields salt plus water, the net ionic is typically the H plus aqueous plus OH minus aqueous yields H2O liquid. If you want to think about, instead of H plus, we said H3O plus is really what we're getting. So H3O plus aqueous plus OH minus aqueous yields 2 moles of H2O liquid. That's another form, and that's actually a little closer to reality in terms of what's happening in water. There's not free protons. They're usually bound up as hydronium ions. Now, because these neutralization reactions are so important and we'll be seeing them so often, we have a guide here to balancing those equations for neutralization. So first, we write the reactants and products. Second, we balance the H plus in the acid with the OH minus in the base. Third, we balance the H2Os that we generate with the H plus and the OH minus. And then 4, we write the salt from the remaining ions. So the cation from the base and the anion from the acid will pair up to form our salt. So it's a 4-stepper, but it's not very difficult. Once you get the hang of it, it follows a nice pattern and gets to be quite comfortable, even though it is 4 steps as opposed to a lot of times we see just 1 or 2-step guides. All right, let's work through one of these neutralization reactions. For this case, we're going to write the balanced equation for the neutralization of magnesium hydroxide and nitric acid. So first, we'll write the reactants and products. So MgOH2 aqueous plus HNO3 aqueous yield H2O liquid plus salt. All right, and so we don't know exactly what salt yet, although I'm sure some of you have already determined it, but that's our generic reaction. We know we're going to get a water plus salt. So that's our products are all going to fall into that category. It's just the specifics of the salt that are going to depend on the specifics of the reaction. Step 2 here, we'll balance the H plus in the acid with the OH minus in the base, and we see here we've got 2 moles of OH minus from the magnesium hydroxide base, so we're going to need 2 moles of H pluses from the nitric acid. All right, and that's going to ultimately form 2 moles of water, but we'll save that for the next step. All right, so moving on to step 3, now's the time to put that coefficient of 2 out in front of the H2O because we've balanced it based on the fact that we have 2 moles of OH minus and 2 moles of H plus on the left. We know we're going to have 2 moles of H2O on the right. Now finally for step 4, we'll write the salt from the remaining ions. So the magnesium 2 plus ion that came from the magnesium hydroxide base plus the 2 moles of nitrate ion that came from the nitric acid form Mg NO3(2). Notice we have to put the polyatomic nitrate ion in parentheses because we have 2 moles of it. If it were just 1 mole, say NaNO3, we wouldn't use the parentheses, but in this case, because magnesium's a 2 plus and we need 2 moles of the nitrate 1 minus to balance, we do have to put them in parentheses. All right, so hopefully now that you've seen it through, the guide is a little less intimidating, and hopefully you get the hang of it very, very quickly. So now that we've talked about the guide and worked an example problem together, you knew this was coming. It's time for a learning check. So let's see how you do on your own. You will write the balanced equation for the reaction of the base potassium hydroxide with the strong acid sulfuric acid. So again, potassium hydroxide is a strong base. Didn't mention that here, but hopefully you remember that. And of course, sulfuric acid is one of our 6 strong acids. So go ahead and stop the video here while you work on the learning check. Once you have the correct answer, please start back up and we'll see how you did. All right, I'm sure you're eager to check your work, but let's go ahead and see how we would do this step by step. So first we're going to write the reactants and products. So potassium hydroxide plus sulfuric acid, each of them in the aqueous phase, yields liquid water plus our salt, our unknown salt at this point. For step 2, we'll go ahead and balance the H plus in the acid with the OH minus in the base, and we see that we get 2 moles of potassium hydroxide to balance out those 2 moles of acidic protons in the sulfuric acid. Sulfuric acid, as we said before, is a strong acid in the first step and a pretty strong weak acid in the second step. When it's combined with a base, a strong base like potassium hydroxide, all of those protons are going to be coming off because the base is going to pull them off. The fact that it would be a weak acid in water for that second step, in the presence of the base, it's going to be deprotonated completely. So there we have it, and we've got those balanced. We're ready to move on to step 3 and balance out our waters. All right, moving on to step 3. Now, since we had 2 moles of OH minus and 2 moles of H plus in step 2, we know we're going to have 2 moles of water here in step 3. And then finally, in step 4, we can look at the ions left over. So the potassium ion was the counter ion of our base. The sulfate ion was the counter ion of our acid. So we end up with the salt, potassium sulfate. And because sulfate's a 2 minus polyatomic, we're going to need 2 moles of K plus. So K2SO4. Notice because we have just 1 mole of the sulfate, we don't put it in parentheses even though it's a polyatomic because we had the multiple moles of potassium here. If we have multiple moles of sulfate, then we would put sulfate in parentheses, but since it's not present in more than 1 mole amount for the 2 moles of potassium ion, it stays without the parentheses. So hopefully that's exactly what you had as your overall, and if that's not the case, hopefully then by going stepwise through that learning check here in our solution, you could find where you may have gone wrong and hopefully won't make that mistake again. If you're still struggling, try some additional problems. We're going to follow up with another learning check right now, but try some more of these. And really, if you're not getting any better on your own, please do reach out for some help. Okay, so as promised, here's our second learning check here on this concept. For this learning check, you're asked to select the correct group of coefficients for the following neutralization reactions. So HCl aqueous plus aluminum hydroxide aqueous yields aluminum trichloride aqueous plus water, liquid water. So where we have those listed, A, B, or C, the 1331 for A, for instance, means you'd have 1 mole of HCl, 3 moles of aluminum hydroxide, 3 moles of aluminum chloride, and 1 mole of liquid water. This is just a convenient way to put this thing in a multiple choice question rather than having to write the the reaction equation every time. So go ahead, see how you do on these two reactions. Stop the video here while you work. Start back up when you're ready to check that work. All right, so for number 1, it's 3 moles of HCl plus 1 mole of AlOH3 react to form 1 mole of AlCl3 plus 3 moles of H2O. So the correct answer was C, 3, 1, 1, 3 for coefficients. For number 2, it's 3 moles of barium hydroxide plus 2 moles of phosphoric acid yield 1 mole of a barium phosphate plus 6 moles of liquid water. So the correct answer is choice B, 3, 2, 1, 6. So if you struggled with that, hopefully it was just a simple issue like not understanding what those coefficients were all about in your answer choices. But if you're still really struggling with the concept, please do try some other balancing problems. And if you're still continuing to have difficulty, please reach out to me for help. Okay, moving along in chapter 10, section 5, we've got acid-base titration. So titration is a laboratory procedure often used to determine the molarity of an acid, and it uses a base, such as NaOH, is our classic base, to neutralize a measured volume of an acid. And so you did have a chance to find the NaOH concentration by doing an acid-base titration in the online lab. So hopefully this is familiar, and hopefully at some point in your educational past you had a chance to do this live using a burette and doing a titration either in high school or in a different college course. But at least you had the experience online with the lab, if not anywhere else. Okay. And if that was probably difficult if you had never had it before, and that's why we had the titration tutorial for you to work. So titration is a classic use of that acid-base chemistry to make determinations about molarity of an unknown acid or an unknown base. We talked earlier about the idea of using a pH meter to determine pH, and that's a good thing, and you could even do that in an acid-base titration, but it's much more convenient to use an indicator. And an indicator is added into the flask that you're going to be titrating into, and it'll cause the solution to change color when the acid is neutralized. So typically, if you look at this particular example, we see phenolphthalein as the indicator, and we can tell that by the magenta sort of color forming in those bottom swirls in the container. And phenolphthalein is a nice one because right when you've neutralized the acid with your NaOH, one more drop will send the phenolphthalein to this permanent pink color to let you know that acid has been completely neutralized by base. We can use other indicators for other applications. Sometimes it makes sense to use a different indicator, but for your classic strong acid, strong base titrations, phenolphthalein is a great indicator. So you know your titration's done when that indicator changes color, but the reason the indicator changes color is that you've reached the end point of the titration. So at the end point, you have your moles of OH minus from the NaOH in the burette equal to the moles of acid, H3O plus in the acid, the unknown acid that you're titrating. And you'll get a faint permanent pink color if you're just one drop over that equivalence point, the end point. If you go much more than that, you get a very intense pink color, but that's not our goal. Our goal is to change it just slightly pink because technically for the phenolphthalein to change, you've got to be just slightly basic. So you're already over a little bit, so you don't want to be over any more than that one drop that sends you over. So again, in that one drop out of 25 milliliters, that drop is not a significant volume, but we don't want to add a milliliter extra and get some really hot pink solution just because we're not careful in our titration. We can get very good results with titration if you titrate carefully and look for that faint, lasting pink color. Now, you can titrate a base against an acid if you have a known acid of known concentration. You could use it to find an unknown base, but classically in titration, we're using a standardized base like NaOH to find the concentration of an unknown acid. And the way we do that is we take that measured volume of NaOH at the endpoint, how much NaOH we had to add to that acid to get equal moles of H3O plus and OH minus. The NaOH we've already standardized against some other acid, typically an acid that would be non-hygroscopic, a solid that we could weigh and it doesn't absorb water from the atmosphere, something like it could be oxalic acid even, or more classically, you've got potassium hydrogen phthalate as our primary standard acid to titrate against. So we know the molarity of NaOH because we've titrated against the standard acid. We know the volume because we've measured it on the burette. We can calculate therefore the number of moles, right? Molarity times volume in liters gives us moles of NaOH. And if we know the relationship between the moles of NaOH and the moles of acid in the flask, if it's a monoprotic acid like HCl, for instance, it's a 1-to-1 relationship. If it's a diprotic acid like sulfuric acid, then it's 2 moles of NaOH to neutralize every 1 mole of acid. And then finally, since we can figure out the moles of acid, we can find the concentration of acid because we know the volume of acid that we took as our sample. So it's a very powerful technique. It's really useful in the lab to figure out these concentrations. And even with all the technological advances over the past 150 years since we've been doing titrations, it's still one of those wet chemical methods that really works well for a human being to do it in this sort of fashion to find the concentration of an unknown acid. Because it is so useful, and because even today it remains a useful part of chemistry, we've got our guide to calculations for acid-base titration. So it's another 4-stepper, but just like the last one, don't be put off. It's not especially difficult once you get the hang of it. So our first step is going to involve writing the balanced equation for the neutralization. We need to know what the moles of base and moles of acid stoichiometric relationship is. That's why we need that balanced chemical equation. Second, we'll write a plan to calculate the molarity or the volume, whichever we happen to be lacking. Third, we'll state equalities and conversion factors, including concentration, because that's going to factor in at least for the base, if not for both the base and the acid. And then finally, we'll set up the problem to calculate the quantity that we need. So pretty classic guide. Just the specifics of these problems will involve those neutralization reactions. So let's take some time to work an example together, and then we'll have you try a learning check. So in this example, what is the molarity of an HCl solution if 18.5 milliliters of a 0.225 molar NaOH solution are required to neutralize 10.0 milliliters of the HCl? So our balanced chemical equation is our first step. HCl aqueous plus NaOH aqueous yields NaCl aqueous plus H2O liquid. So it's a 1-to-1 to 1-to-1 mole ratio. That's great. We can't hope for any better than that. So now we're ready to analyze the problem and look at what we're given and what we need. We're given the volume of the acid. It's given in milliliters. We'll likely convert it into liters because that's our base unit. Same thing for the base volume. It's given in milliliters, but convert to liters so that you can work with the liters and molarity to get moles, and the base molarity is given as 0.225 molar. So what we're missing here, what we need is that molarity of HCl. And we already have our neutralization equation, so we're ready to move on to the next step. All right, so from the previous slide, we have step 1 finished, the balanced equation for the neutralization. So 1 mole of HCl aqueous plus 1 mole of NaOH aqueous yields 1 mole of sodium chloride aqueous plus 1 mole of liquid water. So next, we're on to step 2 now. We'll write a plan to calculate molarity or volume. In this case, ultimately, we're looking for molarity because we're asked what is the molarity of an HCl solution. So we'll start with liters of NaOH. We'll use the molarity of NaOH in order to get moles of NaOH. Then we'll use the mole-mole factor from the balanced chemical equation to relate moles of NaOH to moles of HCl. Spoiler alert, they're 1-to-1 in this case. Finally, we can divide by the liters of solution, moles per liter, right? So divide the moles of HCl by the liters of HCl, and we find the molarity of that HCl solution. All right, so on to step 3, we can look at the equalities and conversion factors we have. So 1 liter of the NaOH solution, because of its concentration given in the problem, equals 0.225 moles of NaOH. So we can represent that with either the liter of NaOH in the numerator and the 0.225 moles of NaOH in the denominator, or the inverse. We also know that 1 mole of NaOH reacts to neutralize exactly 1 mole of HCl, so we can use that mole NaOH to mole HCl either with the mole of NaOH in the numerator and HCl in the denominator, or the inverse. Hopefully you can already see that we're going to want to have that mole of HCl up top based on our plan from the previous slide. Finally, moving on to step 4, now we're ready to plug it all in. So we start with our volume of NaOH. In this case, it's 18.5 milliliters, which is expressed as 0.0185 liters of NaOH. We multiply through by the concentration, 0.225 moles of NaOH per 1 liter of NaOH solution. Multiply now by the 1 mole of HCl over 1 mole of NaOH from our balanced chemical equation. And finally, that will give us the moles of NaOH when we divide the moles of HCl rather. When we divide the moles of HCl by the liters of HCl, we started off with 10.0 milliliters of HCl, so that's 0.0100 liters of HCl. We take our 0.00416 moles of HCl divided by the 0.0100 liters of HCl to get a concentration of 0.416 molar HCl. We can also check our work here because we can tell that it took almost twice as much of the NaOH to neutralize the 10 milliliters of HCl. It took 18.5 milliliters of NaOH, so that means the HCl probably should be almost double the concentration of the NaOH, and we see that here. We had 0.225 molar NaOH and 0.416 molar HCl. So that's a logical check just to make sure that you had your setup correct. But hopefully you did, and we worked through this together, so now you're ready to try one on your own. Okay, as promised, here's your learning check where you're going to calculate the volume in liters of 2.00 molar sulfuric acid, H2SO4, required to neutralize 50.0 milliliters, or 0.0500 liters, of 1.00 molar KOH. And you're given the balanced chemical equation here, and you have a few multiple choice answer selections. So go ahead, work the problem rigorously, and then decide if A, B, or C is the best answers. Pause the video here while you do your work. Start back up once you're ready to check that work. All right, so step 1 was actually done for you, right? Write the balanced equation for the neutralization. In this particular example, it was given to you as 1 mole of sulfuric acid plus 2 moles of potassium hydroxide yields 1 mole of potassium sulfate plus 2 moles of liquid water. So we're ready for step 2 now to write our plan to calculate molarity or volume. In this case, we're actually looking for volume, which is different from the one we worked together. So hopefully that didn't throw you for too much of a loop. We're still going to start with the liters of the KOH, which is again, instead of sodium hydroxide from our example, we're using potassium hydroxide here, but they're very similar. We'll take the molarity of the KOH to multiply the liters by molarity to get moles of KOH. Mole factor, it takes 2 moles of KOH to react with every 1 mole of H2SO4, so we'll have to consider that to find our moles of H2SO4. Finally, we're given the molarity of H2SO4 as 2.00 molar, so we'll use that molarity to find the liters of H2SO4. Moving on to step 3, we can state some of those equalities and figure out how we might be using them as conversion factors. So we had 1 liter of KOH per 1 mole of KOH because it was a 1.00 mole per liter solution of KOH. So we could represent that with either the liter up top and the mole in the denominator, or vice versa. We know that it takes 2 moles of KOH to neutralize every 1 mole of H2SO4 from the balanced chemical equation. And so we can either have the 2 moles of KOH up top and the 1 mole of H2SO4 in the denominator, or the inverse, which is actually the form we'll use because we're looking to convert from KOH into H2SO4, so we need the H2SO4 in the numerator and the KOH in the denominator. So moving on, again, continuing with step 3, we have that 1 liter of H2SO4 equals 2.00 moles of H2SO4, and that's given from the concentration of 2.00 molar H2SO4 from the problem itself. So we can either have the 1 liter of H2SO4 in the numerator and the 2.00 moles of H2SO4 in the denominator, and that's actually the form we'll need to get liters of H2SO4, which is what we're looking for here. Or we could have, depending on how the problem was staged, we could have done the 2.00 moles of H2SO4 in the numerator and the 1 liter H2SO4 in the denominator if we were given a different sort of problem. But for this case, we're going to use the first example there. And finally, in step 4, we can set up our problem to calculate that needed quantity with the actual values. So we get 0.0500 liters of KOH times 1.00 moles KOH per 1 liter of KOH solution times 1 mole of H2SO4 per 2 moles of KOH times 1 liter of H2SO4 per 2 moles, 2.00 moles of H2SO4 from the concentration given in the problem. And if we do that all correctly, we should end up with a result that is 0.0125 liters of H2SO4 solution. So the correct answer choice here was choice A. Hopefully that went very well for you. If it did not go well for you, please do try some other problems and certainly reach out to me for help. We're nearing the home stretch here of the course. We've got just one section remaining on buffers, a very important section, especially for those of you interested in biology or medicine or the allied health fields like nursing. Buffers are critical to how human enzymes can function and how we can have different pH values in our foods that we consume, but a very regular pH value of our blood. So lots to do in that last section. Hopefully you're excited about it. I know I am, and I hope to see you there soon.